All right, where did I put that? Good grief. I can't find anything in here. I don't know. Oh, crap. This is the second of two videos about how computers do subtraction using binary numbers. In the first video, we talked about the ones complement, which is kind of cool, but it has a problem in that there are two different ways to represent 0. This way, the twos complement, what we're going to learn today, is way cooler, and there's only one way of representing 0. Let's get started. Those of you who watched the first part of this lecture might recall that we defined the number b as b is equal to 2 to the n minus 1, where n is basically our word size. And in this case, 2 to the n minus 1 will be just a binary number that consists of just n ones. Okay. Now we're going to define the twos complement of an n-bit number b in the following way. It's going to be 2 to the n minus that number b. But initially, let's think of it as like this. Take to that 2 to the n minus 1. So subtract out a 1 and then add it back. And so we'll have our b minus b plus 1. So we can think of our twos complement as being, okay, take the ones complement, right, this capital B minus b, and then add 1 back to it. So that's one way to think about this. Okay, now we want the twos complement because we're going to be using it to do subtraction. And so let's start out saying we have these two binary numbers, a and b. I'm going to say a minus b. And let's get just a little bit mathematically sophisticated. Let's have a minus b, say this is equal to a minus b plus 2n mod 2n. You may recall that when we put this mod 2n out here, it means we're just keeping the remainder when divided by 2n. So that means if I add a 2n and take it mod 2n, this is just like I am adding 0. Okay. And so I do it like this, and then I can rearrange it. And so this is like a plus 2n minus b and mod 2n. And so this subtraction, provided I limit myself to just the window of the register that holds our number words, it is just like adding this twos complement modulo 2n. And so again, anything that goes beyond our n bits is pushed out of the picture. And so this gives us a very pretty way to do subtraction by doing addition, if we're willing to think modulo 2 to the nth power. Okay, so what we have here is a table of binary numbers. The first column lists out the numbers from 0 to 7 in decimal form. Okay. The second column, I've put them into binary representation. The third column, we have the ones complement, which again, the ones complement is easy to take. Again, thinking about it, you just flip each individual bit. I mean, that's an easy machine operation. And so if I look at any number in the ones column and it leads with a 1, that means this is a negative number. If I want to know what it's the negative of, I just flip each of the bits and get it back to its original form without the leading one. And so this one I can tell, this is 0. I can go back here, flip all the bits on it, and that was 4, and so forth. Okay, and so that's very important to not only be able to get your negative number, but to know what number that's the negative of. Okay. Now we have the 2's complement. We go over to the 2's complement. We take the 1's complement and just add a 1 to it. And so that's an easy arithmetic operation. We could design our adder to do it that way, or some system to make this switch just to add in a number. But if I look at my 2's complement, it's not necessarily transparent what this is the negative number of. Okay, so let's look at this a different way to see. So a quicker way of finding the 2's complement is to look at your binary number and find the rightmost one if it exists. And if there is no rightmost one, that's 0. You're there. Okay. Here, find my rightmost one and point at that, and then every bit to the left of that, you flip it. Okay. And so this number here, which is what? 4 plus 2, this is 6, right? If to get the negative of it, I flip all of these bits, I get 1, 0, 1, 0. Now let's look back at my chart. Is that right? 1, 0, 1, 0. Yes, that's the negative of 6. Okay. Now, the thing about this operation is that it's a toggle. Okay. I can go and say, look at this number, right? Find the rightmost one. Got it. Toggle everything to the left of that, and we're back to where we started. Okay. So when I think about obtaining my 2's complement in this way, it's very easy to get back to what is this number the negative of. Okay. All right, let's do a couple of examples just for proof of concept. My first one, I'm going to be taking 3 minus 7. And 3 is 0, 0, 1. 0, 0, 1, 1. And negative 7 is 1, 0, 0, 1. Okay. Then I add these together. 1 plus 1 is 0, carry the 1. 1 plus 1 is 0, carry the 1. 1 plus 0 is 1. And then I had the 0 plus 1 is 1. And so this is my number. I look at the rightmost one and toggle. Okay, toggle everything to the left of it. That would give me 0, 1, 0, 0, which is 4, meaning that this number is indeed negative 4. Okay, now I am going to take 7 minus 3. Okay, 7 is 0, 1, 1, 1. Negative 3 is 1, 1, 0, 1, and then I add these together. 1 plus 1 is 0, with a 1 carried. Carry the 1. 1 plus 1 is 0 with a 1 carried, so bring down the 0. Then I'll have 1 plus 1 plus 1, which is a 1 with a 1 carried, and 1 plus 1 is, you put down a 0, and you have 1 left over, which which goes and disappears out on the left-hand side. Okay, and so if this were if I were adding two numbers instead of subtracting, this would be an overflow error. Okay, but with the system set up as this is a subtraction, it's not a problem. And so now I have 1, 0, 0, which is 4, which is the same as 7 minus 3. Well, I hope you enjoyed that, and I hope you understand a little bit better now about how computers do subtraction. In the future, I may make some videos about how computers do multiplication, but that'll wait for another time. In the meantime, if you enjoyed this, click the thumbs up button if you liked it, and you might think about subscribing for similar content. Yeah, who is it? No, I'm not doing anything. Come on in.